So anyway, good morning, everyone. There are enough people here, almost 11 students. So let us start today's session. In the last class, what we have seen is we have seen the asymptotic analysis. That is the first notation, which is known as big O notation. Big O notation says that it has to there is a function f of n, and that function is less than equal to some constant c and another function g of n. Now in the same way, so we have last class, we have seen one of the asymptotic notation, that is big O notation. Now in the same way, let us continue with the next notation known as big omega notation. And this big omega notation actually is very much similar to big O notation. The only difference is that there is a function f of n which increases as the size of the input increases. That is, input is on the x-axis and the y-axis has the random time. So as the input size increases, the function f of n, which is a time function we are saying, increases. Then there is another function known as g of n function. So in big O notation, g of n function is above f of n function for some n value. But here in big omega notation, it is below. So what we say is f of n, instead of less than equal to, we say f of n is greater than equal to c of g of n. So f of n is again a function. We know that for an algorithm, the steps we count and those steps are the number of times an instruction executes. That is considered, we take that as a function, and a function of n, where n is the input, and we try to evaluate the asymptotic notations. So here, big omega notation says that f of n, there is a function f of n, which is always greater than equal to some constant c and g of n for n greater than, for some n greater than n0. Now even here, c, which is a constant, it should be greater than 0. C is a constant, it cannot be negative, it should be greater than 0, not even equal to 0, because if it is equal to 0, then the function, whatever function g of n is, it will be 0. So c should be greater than equal to 0. And then n0 is the input, n is the input actually, so n0, initial input n0. We start with some input which should be greater than equal to 1. Now always remember, I told you in the last class also, input is always greater than equal to 1 because there should be at least one input. So n should be at least 1. So now if this is true, that is f of n is greater than equal to c of g of n for some n greater than equal to n0, then we call this as the function f of n is omega of g of n. Now we said f of n is big O of g of n. Now let us talk about f of n is omega of g of n. Now when this is true, what happens? Now what we have is, let us assume we have the same function last time we have seen, 5n plus 4. There is a function 5n plus 4. Obviously this function 5n plus 4 may have been derived from the the steps and number of times an instruction executes for the algorithm. Now let us assume that g of n should be n. Now remember always, function f of n is there is another function g of n. So f of n is 5n plus 4, and let us assume that g of n is n. And this g of n function will not have anything plus some constant or anything else. It's a simple expression without any constants. So we have to prove that f of n is greater than equal to c of g of n. Now here, c should be greater than 0 and n should be greater than n0. That is here, greater than n0. So now suppose if we take the function becomes f of n plus 4 greater than equal to c of n. Here 5n plus 4 is nothing but f of n function, and n is g of n function. Now suppose if we take c equal to 1. This is one of the possibilities. There can be many more possibilities. So if c equal to 1, what happens is 5n plus 4 is greater than or equal to n. So this happens for what value of n? N0 equal to 1 itself you take it. I mean, here itself we can say, I mean, if n is taken as 1 or n0 is taken as 1, here itself we can say that this is true. So for the value, for the constant c equal to 1 and for n equal to 1, then we say that, I mean, we are proving that f of n function is greater than c of g of n function, where f of n function is 5n plus 4 and g of n function is n. So we can say that f of n is big O of g of n. So what we can say is f of n, when we are saying this, f of n is big O of g of n, we are saying f of n is 5n plus 4, which will be equal to not big O, omega of n. So omega of n is nothing but omega of g of n. G of n is we are taking n. So we can say that this is omega of n. So that's how we say, or we define omega notation. Now here, only difference between omega notation and big O notation is big O notation has f of n less than equal to c of g of n, cg of n, and omega notation has f of n greater than equal to constant c g of n. So this is what is the omega notation. In the same way, what we can, we have something known as the, for example, for big O notation, what we said it is the upper bound. It gives us the upper bound till the maximum what can be, the bounding or the limit is. Whereas omega notation gives us the lower bound. That is, any algorithm cannot perform below this. Big O notation is any algorithm cannot have the complexity more than the upper bound, whatever we are saying. Same way here, big O notations cannot have, algorithm cannot have lower than this f of n. So this was all about the lower bound, or the what we say big omega notation. Now, in between this upper bound and lower bound, we have something known as the tight bound, or we call it as big theta notation. Big theta notation. Now, big theta notation is between the upper bound and the lower bound. So it is between big omega notation and big theta notation. So when we consider f of n, and let's say function f of n, which increases, the running time of this function increases as the size of the input increases. Now we have this c1, another function g of n, which is with constant c1. Now this is lower. So f of n is greater than c1 of g of n, means this is the omega notation. Now, in the same way, if there is a function g of n, same function g of n, but with a constant c2, which is greater than the f of n function. So this is greater than f of n function, but some input n0. This n0 should be greater than some value. So this c2 g of n and f of n is nothing but our big O notation. So here that is what we are saying. F of n is greater than c1 g of n, this one, and f of n is less than c2 g of n. So this part over here is your omega notation, is your big O notation, and this part over here is your omega notation. So theta notation is between the upper bound and the lower bound. So when this is true, what we can see that there is two different constants, C1 and C2. And these both constants are greater than 0. Like in other notations, we said C is greater than 0. Same way here, these both constants, C1 and C2, are greater than 0. Then this n0 should always be greater than equal to 1. Now we say that f of n is theta of g of n when f of n, let us say that we have 5n plus 4 is less than equal to c of n. G of n is n itself over here. Now we have seen this when C in big O notation, that C2, when C constant value is 6, N value will be 4. So greater than input 4, this equation satisfies. The same way, we have seen f of n is plus 4, f of n is greater than or equal to c of n, that is 5n plus 4, that is 5n plus 4 is greater than or equal to c of n. Now, this is last slide we have seen, the previous one, when c becomes 1, that is in this case it's c1, n0 should be 1. So, here we have C1 and C2 instead of C, and for C1 we have 1 value as 1 and C2 value as 6. If we substitute this in the equation, we can say that f of n is 5n plus 4, which is equal to, or which is asymptotically, we can say that, equal to big theta notation or theta notation, theta of g of n, where g of n over here is n value itself. So f of n is asymptotically equal to theta of n, and this is known as tight bound. Excuse me, this is known as tight bound. So big O notation is the upper bound. No algorithm, or not algorithm, let's say function, because we are talking in terms of mathematical equations. So in asymptotic notation, big O notation is big O notation is the upper bound. No function can have or have the performance or running time more than that. Big omega notation is the lower bound. No function can have running time less than that. And tight bound or big theta is between upper bound and lower bound, that is between big O notation and omega notation, and is known as theta notation or the tight bound. So this is what was with respect to the asymptotic notations. Now, when will these notations be useful? Now, earlier I have shown you one slide in the previous sessions. Just let me retrieve that slide. Where was that? It's not visible. Okay, anyway, it doesn't matter. But I don't have that previous slide right now because it's there in the previous two sessions, previous session. I think in previous session we've discussed that we have three cases in terms of analyzing the algorithm. One is the best case, the other one is the worst case, and the third one is the average case. Now, the best case, for example, if we take a linear search, that is searching an element from the collection of elements. So what is the best case? We have talked earlier that the best case is nothing but the element we are trying to find is the first element in the collection, in the array. So if it's the first element, we find that element and we don't have to traverse the entire array. That's the best case. Now, worst case might be the element we are trying to find is the last element, or that element is not present itself in the collection or in the array. So if it is last element, we have to traverse till the end, that is till the last element. And last element, if it is found, then we say we return it's found, or else if it is not found, if element's not there, even though we have to traverse till the end, and then after traversing till the end, we say it's not found. So that's the worst case. Then what is the average case? Average case is nothing but any element is found somewhere in the middle. Now this best case is very easy. Worst case is also very easy, but it is not easy to determine the average case. So anyway, what we mean to discuss over here is that best case is nothing but omega, big omega notation. Now that big omega notation is the best case. And when we devise an algorithm, when we analyze an algorithm, we are not bothered about best case. But omega, just anyway, sorry for the disturbance. There was an urgent call. So anyway, let us continue. So what I was saying is, we have three notations: the big O notation, big omega notation, and big theta notation. Big omega notation is the lower bound. So we say that it's the best case. So to represent the best case, we use big omega notation, saying that an algorithm is omega of n. If we say omega of n, what it means is no algorithm can be less than that, can take less time than that, can consume less time than that. So for best case, we represent generally, we use omega notation to represent. Now then, what about the worst case? We are actually not bothered about best case. When we analyze algorithms, when we design and analyze algorithms, we are bothered about the worst case. That is, how will an algorithm work in worst case scenario? What will be its time complexity in worst case scenario? What is its performance in worst case scenario? So what we do is we generally consider the worst case scenario. So big O notation is the upper bound. Remember that it's used for upper bound. So upper bound means it is actually big O notation. So worst case of algorithm are done in big O notations, are represented in big O notation. What this means is, if an algorithm is big O of n or big O of n square, no other algorithm can perform better. No other algorithm, that same algorithm cannot, the time complexity cannot go beyond this worst thing, that is O of n or O of n square. So that is what the worst case we generally case we use theta notation. To describe an average case, we use theta notation because theta notation is the tight bound. That is, it is between the lower and the upper bound. So we use theta notation for average cases. Anyway, we would not be interested about average cases also because it's much difficult to predict that. We are most interested in the worst case scenario. So that is why generally we use big O notation for worst case. Or you can find that from now onwards, whatever algorithms we will talk about or whatever the complexity we will talk about in terms of big O notation, O of n square or O of n cube, O of log n. So we talk about the functions or the algorithms in terms of big O notation, because that gives us the worst case scenario. But sometimes what happens is the best case and the worst case are same. That means even if you take the average case, it will be same. So that time also, because big O notation tells us about, we can use big omega notation also, but in general we use big O notation itself. So most of the time, and textbooks or articles, or when we talk about algorithms, we compute or we represent the time complexity or the performance of the algorithm in terms of big O notations, because that gives us the worst case scenario. So this was all about the three different notations. So anyway, now we will move further. So we have seen what an algorithm is, how we devise an algorithm, the steps how we translate that algorithm, that is an informal, using the informal language for the solution. We convert that into a formal language as an algorithm using pseudocode, and then that we take some data structures that like arrays or some statements, loops and all, and we compute the we make the we devise an algorithm, and then we compute how many instruction an algorithm uses, or how many times an instruction is repeated in execution, and we come with the what do you call a priori estimates or theoretical analysis, and we compute the number of times an instruction runs on an algorithm runs in terms of a function. We call that as a time function, or f of n function. So some mathematical function, which is a polynomial generally. And then we have seen what are three notations. We have also seen the space complex. Now let us move further with some of the basic data structures or elementary data structures before we move on to the complex algorithms in this subject. So we will start quickly with the stacks and queues. Now this stacks and queues you may already have seen in your data structures in second year, but let us revisit this. Now on your left hand side you have something known as stack. Stack, as you all know, or the term how a stack is defined, the one end of the stack is closed and the elements or the items can be inserted only from one end. That is known as the top of the stack, and it works on the principle of last in, first out, LIFO. Last element which is inserted, that is the element which is taken out. Then comparing with the queues has both the ends open, and the elements are inserted from the rear end and elements are removed from the front end. Now, though, you can remove the elements from the rear end and insert the elements from the front end, but usually, or the way we proceed or progress, the way for flexibility, what we say and how the queues are defined is the elements are inserted from the rear end and removed from the front end. Now let us quickly look at the algorithm. The operations of stack operations, which are defined in terms of pseudocode. That's what we call it as algorithm. Now here we have the algorithm as add. You might have heard about the term push in your data structure, that is pushing an element on the stack. Now here in the prescribed textbook, what we have for design and analysis of algorithms, there the term add is used. So that doesn't matter. The functionality is same whether you are pushing an element or whether you are adding an element. In both the cases, you are inserting an element in the stack. Now, since this is the array-based representation of stacks, that is, we are taking array to hold the elements of the stack. So therefore, the very first case in the algorithm is we have to check if the stack is full. That is, if the stop reaches n minus 1 or greater than reaches n, or if it is greater than n minus 1, that means the whole capacity of the stack is full. That is the array what we have. Top has exceeded. Top is nothing but the index has exceeded their capacity, so we cannot insert the element. So we say that stack is full and we return false. That is, cannot push an element or we cannot add or insert an element in the stack. Now suppose in this case, if you see there are few more elements empty in the stack, so we have else. So we increment top index. So top, instead of pointing to this element, top is in moves to the next index. So this is over here, and then stack of top. Remember, assume that this array, the name is stack. Stack of top equal to item. That is the element we are inserting. So here we will insert. Let's say, suppose we are inserting 100. So top we have incremented. So top will now be pointing to, at this cell, and 100 will be assigned and return true. That is what how the push operation happens or add operation happens. Now, before we move further, let us compute the time complexity of this add algorithm. What will be its time complexity? Now, can anybody reply? First of all, you need to know that you need to remember how to proceed. Now, earlier functions, when we found the time complexity, what did we do? We counted the number of steps or the frequency of each statement. So can you compute the time complexity, or let's not say compute the time complexity, let us say frequency of each iteration. Sorry, not iteration. Frequency or number of times each instruction gets executed. Can you do it? I'll show one example. Let's again go. What do I use here now? I want to write something. Is open mode here? Okay. Open mode is there. What do I do? Show the desktop. Okay. Now what do I do? Okay. Now here itself I'll just start scribbling something. Now this is going to take how much? 1 times. It will get executed once. Now if this is true, then this also will get executed once. There is no loop, remember. Here also it gets executed once. And we are not worried about these things, we are worried about these statements. This is statement, this is a primitive statement. It will execute only once. This is also a primitive statement. This also will execute only once. Return, it's a primitive. It also executes only once. So what is the total? 1, 2, 3, 4, 5, 6. So here we have 6 as the total. So if we consider this as a function f of n or time function f of n equal to 6, that means what? What is 6? This 6 is a constant. So we can say that this algorithm of inserting elements in the stack is taking O of 1. Sorry. How do I rub this? It's taking O of 1. That is, this algorithm takes constant time, O of 1. Let me, where is the, okay. ये क्या आ गया भाई? How do I exit this? Okay, anyway. So this was O of 1, constant time. Then let us look at another function. So as we had a function known as push, the same way we have a function known as pop. So what is this pop function doing? The purpose here we say delete because the algorithm in the prescribed textbook it says delete, but delete and pop functions are both same. Just the name is there. Functionality is same. Absolutely, there's no problem. Now here, if we look at this function, I'll use a pen to write something over here. Now this function we need to see if top is less than 0. If it's less than the 0, that means there are no elements in the stack. So we write stack is empty and we cannot pop anything. We cannot delete an element. We can delete only an element which is there in the stack. So when top is less than 0, nothing, we cannot delete it. If not, then stack of top. What is top? Pointing to this. So 15 is retrieved in an item. Then top will be this pointing. Top will now be pointing to this statement at this step. Then we return true. That is the element is deleted. So this is how your delete function or pop function or pop operation works for stacks. Now, can you compute the time complexity of this function? Just anyone tell me the time complexity of this function. We have already seen and demonstrated earlier classes also we have seen. I mean, now also we demonstrated in the insert or the add method, add operation or push operation of stack. I have demonstrated how to compute the time complexity or the frequency of operations. Now you just tell me what is the time complexity. For the first statement, if top less than equal to 0, how many times does it execute? Just anybody tell if you are awake or if you are listening. Just tell me. How much time will it take? How many number of times this statement executes? Anyone can unmute himself or herself and say. Or just type it in the chat box. How much time does it take? It takes 1 unit because it's a primitive statement. A write statement, short statement is also primitive, takes 1 unit. Even this takes 1 unit. Then this statement is also primitive, takes 1 unit. There is no loops here. Even this is primitive, takes 1 unit. Even this is there, takes 1 unit to compute. So total is again 6, for which we can say that f of n of 1, which is constant. Because 6 is not taken, this 1 is taken as a constant. So this is how stack works, or stacks, two operation of stacks work. Now we have seen these two operations of stack on the operations of the stacks when stacks uses arrays. Now we can represent stacks also in terms of linked list. But I think there was no response from the other side when I was asking some questions. So I think we will end the class at this juncture. And continue in the next class. So anyways, if you have any questions, just ask me. Otherwise, we will continue the next session. If there are no questions, then please log off.